on the road!
For our final project, our math class took a van ride out to the main road and back. Every 5 seconds we recorded the velocity of the van, the distance it had traveled, and the amount of pressure Bill was putting on the accelerator. After the drive, we modeled the data with a series of graphs.
So on our trip we measured the velocity, which is the speed we were going, which you can see on the green line. We also measured the accelerator, which Bill indicated by moving his hand up and down to show if he was putting a high amount of pressure on the accelerator or a very low amount. And that's this red line here. And then we also measured distance, which is the blue line.
So here we have this very similar graph, only it's in relation to Chewonki. You can tell right where we turned around, which is right here at 220 seconds approximately. You can tell this not only from the distance, which is at its peak and then heads back to Chewonki, but also when the velocity reaches its, which is 0.
It's a critical point, and we can see that because the velocity, which is the derivative of the distance, crosses the x-axis and changes signs. And this critical point is shown to be a maximum because you can see that the distance reaches its max here and then goes back down.
Next, what we did is we calculated the antiderivative of the velocity to calculate the distance we were from Chewonki to later compare it with the distance we were recording on the trip. This here is the velocity in miles per hour that we recorded as we were going. This is the calculated distance from Chewonki, and this is the calculated distance from Chewonki in 0.1 miles to better go on our graph. We wanted to take the instead of taking the antiderivative algebraically, which we couldn't do because we didn't have a function to match the crazy and fluctuating velocity of our trip, we did it numerically as best we could. We presumed that the car was moving at each of these velocities for 5 seconds, the 2.5 seconds before we recorded it, and the 2.5 seconds afterwards. So we then divided the miles per hour of this velocity by 720. The velocity was in miles per hour, and we had to convert that to miles per second to get the distance that it would have traveled in 5 seconds. So we divided by 720 the number of 5-second intervals within an hour. Then once we had this calculated distance, we multiplied it by 10 to get the distance in 0.1 miles.
One point of error with this is that you can't presume that the car was moving at one velocity for 5 seconds and then at another entirely different velocity for the next 5 seconds. So as you can see here, the graph of the velocity looks like a bunch of really sharp turns and straight lines. Actually, because the car has to be going in one fluid motion, it would be more like a set of curves. But because we can't represent that with our intervals, it looks like straight lines. So you can see as it decreases down to this velocity from here, it would be more like a curve. And so there would be a velocity in the middle that it would be going in the middle of that 5 seconds.
This is a graph comparing the distance that we measured when we were actually in the van, the blue here, versus the calculated distance that we calculated using the antiderivative of the velocity, which is the outside or red line here. Because the distance calculated using the antiderivative of the velocity matches our measured distance so well, that's evidence that we went out the same amount of distance that we did on the way back.
So from the velocity data, we calculated the change in velocity from subtracting a previous point by the current point, and then dividing that by 5 seconds to get miles per second squared, which is the acceleration. The second half of the acceleration data, we multiplied by -1 to get it in absolute terms. We did this because the second half of our velocity data represented the trip back, which made it negative. So in order to get our acceleration data all in the same scale, we had to multiply the second half by -1.
This is what we got from that. We compared the acceleration, the absolute acceleration we had just calculated, with the accelerator data that we had that we recorded during the drive. The purple here is the acceleration, which you can see fluctuates a lot more than the accelerator, because the accelerator we were measuring on a scale from 0 to 2, which was very limited compared to the acceleration, which was much more complex. This allows us to see a few things really clearly. First, we can see here where the acceleration varies extremely, This was the point at which we got to the stop sign and turned around. That's what represented that huge change. Also, you can see here that the red is only positive because that's all we could see, while the acceleration data goes really negative, decelerating the car at a rapid rate. These deceleration points mainly resulted from times when Bill had his foot on the brakes, but couldn't show that using our scale.
You see, you can use this if you look really closely to tell specific places we were on the drive. Take this for example. Here we have a deviation between the accelerator and the calculated acceleration. This could be an example where Bill wasn't putting any pressure on the accelerator, but the van was actually accelerating. Maybe it was on a downhill or something like that. Here's a different example. Right here, Bill's foot was on the accelerator, but it turns out the van was actually decelerating. That might mean we're on an uphill or something where he's giving the van a lot of gas, but it's not going very far, very fast.
In order to calculate the average velocity, we added up all the velocities over the intervals and divided by the number of intervals. And the number that we got for the average velocity was 33.886 miles per hour. In order to find at what points on the trip we were going that exact speed, we graphed a line showing 33.886 miles per hour. And you can see where it intersects the velocity are the approximate points at which we were going that speed. It is impossible to determine exactly what points we were going that speed because really it would be more like a set of curves instead of straight lines. But you can see it's around here at 20 seconds, at 60 seconds, at 65, and so on. And we knew that it would cross this at some point because of the mean value theorem.
Now I'm going to explain a little bit about the mean value theorem. The theorem basically states that at some point C, between two other points A and B, the derivative, or the velocity, is equal to the average velocity within that interval. So we know that no matter what is happening between A and B, at some point the velocity C, the average velocity is going to be reached at some point, represented here by C, depending on these different curves.
As you can see on the velocity graph, we reached maximum velocity at 345 and 395 seconds, and that velocity was 50 miles per hour. However, it's kind of impossible to tell when exactly the highest velocity was reached, as the car could have accelerated and decelerated within a 5-second interval, with that change not being measured.
If you look at these two maximum velocities that Eleanor was talking about, you can see a sharp increase followed by a decrease in both cases right before in the acceleration graph, the derivative. If you look carefully, you can tell that when you reach these maximum velocities, the derivative is at 0 in acceleration, making these two critical points. That makes sense because when your acceleration is still positive while your velocity is still increasing, but as soon as it becomes negative, you start losing velocity. Hence, we have maximum velocity points. Thanks for watching!
We had a lot of fun with this project.
And we learned a lot about derivatives.
Sorry for handing it in so late.
And thanks for your understanding.
Bill and Steve will miss you both so much next year.
And Bill, since we know you're leaving, we wanted to say,
We wish you luck in whatever you do, and just know that
Chewonki will never be the same without you.
I was sitting in the front. Yeah, whatever. I'm Bill. Get in. You have
Because they match up so well, that's evidence that our velocity... No, damn it. Because the distance calculated using the antiderivative of the I don't have it! Because the distance...
no. A lot of fun. Surprising, but true. Bye.